what they want it to be able to do is have dynamic range in terms of like the colors. This comes down to the way that you remove the noise, but how does this work mathematically? Welcome everybody to Archive Dives with Oxen AI. Today we're going to be going into the Flux series of models, which doesn't have a paper itself, but they have mentioned a lot of different papers that they've worked on in the past. The team who built this fantastic generative image model is a team that's ex-Stability AI folks. So you'll see a lot of their work is inspired by the Stable Diffusion work, and they link to a bunch of different papers that contributed to building the Flux model that we see and love today. The paper that we're going to deep dive into specifically is Rectified Flow Transformers. So this one has a lot of the key concepts, and they have open source code for this model, and people have dove in to the code base, kind of like looked at the architecture, and it's most similar to this rectified flow transformer model. So that's what we're going to be diving into. So if we look at this paper, it is from the team at Stability AI, and it came out in March of 2024, so earlier this year, and has really impressive results. This is also known as the Stable Diffusion 3 paper. So if you're just searching for Stable Diffusion 3, it has a more technical name in the paper, but that's what this paper is. And you can see everything from just like generating realistic text in the images to a bunch of different styles. This model really was blowing out both closed source models and open source models out of the water. And this is kind of the backbone that they allude to using in Flux. So how does it work under the hood? Let's see, I've got my notes over here. The first thing that we need to dive into, and we have covered these in past dives, but just let's get a refresher on what diffusion models do and what this rectified flow means, and then build our way up. So they say that rectified flow is a technique that connects data to noise in a straight line. So what does this mean? As a refresher, all diffusion models kind of go from random noise plus a prompt to a realistic looking image. And so today, the image that we'll be using for an example is this cute little dog on a surfboard. And basically the diffusion process looks like this, where you have training data that is the real images. And in the case of like conditioned diffusion models, you also have text pairs that goes along with that. And what's cool is you can pretty much just take random noise, apply it to the image over and over again until you get this super fuzzy looking image. And then the process of diffusion is just subtracting the noise from the noisy image until you get like some signal, some noise. You then subtract that, you have the model learn how to subtract that noise out, generate the next iteration, generate the next iteration, and slowly over time, you get to pure signal, like a real image, and hopefully no noise. And so in this paper, there's actually a lot of math that looks pretty intimidating if you're just like scanning the paper. Specifically, if you kind of dive into section 2 here, they talk about a lot of these ordinary differential equations, ODEs. As you're scrolling down this side, you're just like, oh my God, this is all Greek to me. So we're going to dive into this equation right here and try to talk about it with the example of the dog on the surfboard to try to make this all make sense. So let's start with like the innermost part of the full loss equation. We're talking about specifically this portion over here. So this epsilon, theta, z, t minus e, absolute value squared. So basically all this is saying here, this is like the subtraction of the noise from the image itself. Okay, so this is like the first part that we have to wrap our head around. And it's basically just how much noise did the model predict? And then we're going to subtract that out and do like a mean squared error on the noise versus the actual image. And so they talk a lot in this paper about the importance of what that noise schedule is and kind of like how you go from the noise to the pixels themselves. And this kind of, whoops, that's not the one I wanted to copy. This step, they say it's really important to have the proper noise sampler and the sample steps. And they even took inspiration from this paper called Common Diffusion Noise Schedules and Sample Steps Are Flawed. And this paper talks a lot about how in the early stable diffusion models, you kind of got these washed out images that never really were super bright or super dark. They were kind of like in the middle. And what they want it to be able to do is have a more dynamic range in terms of like the colors that it can generate. And they argue that a lot of this comes down to the way that you remove the noise from the image, which makes a lot of sense intuitively. But how does this work mathematically? So if we look at the equations they have in the paper, they call this flow trajectories that we're trying to optimize. So this is where like all the ODEs and stuff are coming in. And but from like an intuitive level, let's think about what we're trying to do at each pixel. So at each pixel, we are trying to decide which kind of direction we need to move that pixel value to look more like a realistic image. And so you might have a bunch of different, or you do have a bunch of different pixels here, and you're trying to figure out which way to kind of remove the noise from the R channel, the B channel, and the G channel. And they call these like the velocities of which direction you're going to move that pixel. And so in like ODE land or differential equation land, it's hard to go in just one shot to the correct spot. So what you often end up doing is you can take a bunch of different steps to get to the right place and kind of course correct along the way. This is called like Euler's method to be able to estimate a curve or be able to get to one point to another. And what they say in this paper is they just want that trajectory to be as straight of a line as possible. So instead of doing like a big curve to get over here because it's harder to course correct, they're trying to optimize the model to go straight in that velocity. So although there's like a lot of fancy math and uh, a lot of deriving they do of that, the rectified flow is actually like a pretty straightforward function here. It's just a linear function. It's a straight line. And intuitively, this Z is the noise that you have. This T is the timestamp you're at. The X is the data itself or the image. And then the T epsilon is the noise that you're trying to remove. And so if you think of T equals 0 in this equation, so like time step equals 0, you're all noise, that's going to make this variable go to 0 and this half of the equation go to 1. So like when T equals 0, you want to predict a lot of noise. And then when T equals 1, 1 minus 1 is 0. That puts this half of the equation to 0. And T epsilon is how much noise you have left. So when T equals 1, hopefully you're removing little noise. So that's rectified flow. It's actually quite simple. There's just a lot of math they do to get there. And they actually, in the paper, they compare it to a bunch of other equations within here. Like they have EDM, they have cosine, they have a bunch of different LDM linear, and they benchmark all of these different functions as the kind of sampling schedule that they have. And this RF variant just consistently performs better. So in this case, you can see the RF are the green lines, and they consistently are more sample efficient than the other ones. So I won't go into the other equations, but just like conceptually think about, you just want a straight line from going from that noise to the actual image itself. That is kind of like the inner part of this loss function right over here. That's how we get the Z. That's how we then do the mean squared error on how much noise there actually is versus how much noise you predict. But there's also these interesting parameters that they kind of have on the outside. And so basically this first half of the equation is just summing over all of the noise values at all of the different timestamps and then taking the average and making it negative. But this portion right here, I thought was pretty interesting as well. So the lambda parameter here is what is the signal to noise ratio at that time step. And then the WT is a weighting function depending on what timestamp you're at. And so again, some like fancy math here, but intuitively, what they're saying is depending on what timestamp you're at, if you're kind of at the beginning of the process or the end of the process, it's much easier to either predict a lot of noise or predict very little noise. But it's kind of when you're in this very middle step. So if you think about, when you're at the first timestamp, you predict a lot of noise. If you're kind of in this middle step, you kind of have even signal to noise, so it's harder to tease out what you want to predict. And then if you're at the final step, there's not a lot of noise left, so it's easy for the model to predict that side. And so what this W equation does is really balance out the middle and say, hey, I know you're kind of in this middle state where it's difficult to know whether you're predicting noise or signal. And so this function here just kind of helps it weight those middle stages higher. So it's like pay more attention to the signal versus noise in this step. So that's kind of like intuitively what we're doing there. And so you put that all together, and like this really complex looking equation is really just like how well are we predicting the noise? How well are we predicting the noise in those middle time steps, like really weighting those middle time steps better, and then averaging that over the entire sequence. And that's the loss function. So what we kind of showed at the top of going from the image to noise and back to the image isn't quite what these newer diffusion transformers do. So they're all called this class of latent diffusion transformers. And all that means is like, instead of going from the raw pixel values to the raw pixel values, they have this pre-trained autoencoder in the middle that'll take the image, collapse it down to a latent space, and then reconstruct the image from the latent space. And all of these models, you typically use like a pre-trained autoencoder that's separate from the diffusion modeling step. And you can just grab these off the shelf, open source. I forget the exact one that they use in this paper, but a lot of people use the same ones. And instead of diffusing in pixel space, they diffuse in the latent space. So, before intuitively we were talking about pixel to pixel and trying to get that vector to predict the noise directly in the pixels. What's really happening in this case is you have like this latent vector, which is much smaller to work with, and then they're diffusing the latent vector. Sorry, this is kind of too big to see, but you're kind of randomizing these numbers in that latent space and then trying to predict the noise in the latent space instead of the actual raw image space. And then what's cool about that is that's more computationally feasible to do in the latent space. And then if you do it well, uh, going from latent space to noisy latent space and then back. So you start with a noisy latent space, you generate a more realistic one, and then you use that same decoder to decode the image. This is what a latent diffusion model looks like. So it's not in pixel space, it's in the latent space. And this is where, when we start getting into the diagrams of the model architecture itself, this is where the model sits, and then just recognize that there's like an autoencoder sitting outside the diagram that we're looking at. So now you have some intuition on diffusion, latent diffusion models, and just the rectified flow of trying to make the noise be a straight line to where you actually want to go. So putting that all together, we get a rectified flow transformer. And the first thing to notice here is we have this big old diagram within the paper. And so, like I said, this is going to be like right in here, sitting right in here. And the first thing to notice is there's kind of like two paths that the information can flow down. So you kind of see these parallel lines here. And half of the model weights is for the text side of things, and half of the model weights is for the image side. So we've gone over diffusion transformers in the past, or DIT, and basically the DIT just had the image channel. And what they're doing here is calling these blocks MMDITs, so multimodal diffusion transformers. And basically what they do is they encode the text using clip models and T5. It's kind of interesting in this paper is they combine 3 different text models and 3 different text embeddings to try to get like a variety of textual features into the model. And then they pass that in, they combine it through linear layers, pass that into this multimodal diffusion block. And then within the diffusion block, they're doing the same thing on the other side with all of the image patches. And then they have some cross attention that lets the image tokens and the text tokens communicate back and forth. But these 2 channels are trained kind of in parallel, one to encode information about text and one to encode information about images. And then you'll see they have the other types of things that you pass into diffusion models, like the time step that you're at, some encoding of that time step, and then the noisy latent space that you start with. So how it kind of like combines the caption that you want to generate and make it unique every time is they have this just random noise latent space that they pass in. They take the text, encode the text into, there's like up to 77 tokens, encode it with 3 encoders, and then they combine all that information together, do the diffusion process over and over in the latent space, and then they'll get a vector out that looks like this, that they'll pass through the decoder of the autoencoder, and then magically you get an image out the other side. So that's kind of the first architectural difference, is just the 2 paths for the images and the text to come through. Like I said, this paper wasn't the Flux paper, but somebody on Reddit did a diagram of the Flux paper. And so you'll see it's actually very similar. It's just kind of like flipped on its head. And so you have a text prompt that comes in, goes through the cliff, goes through the T5 encoder. Um, those get passed through like slightly differently, but you still have kind of these two parallel paths going through the model. You still have the attention mechanism going between them. It looks like they're using slightly different positional encodings. And then finally, it goes up through another transformer layer and then through the VAE. VAE is just variational autoencoder to decode the image. So very inspired from the paper we're going through today. But there might be some slight differences in the underlying implementation, and they have open source code that you can look at to figure out the nitty-gritty details there. In terms of the data sets they try this on, they use ImageNet plus CC 12 million. And so ImageNet is like 1.4 million images with labels, and they basically just generate a smaller set of the training data by saying a photo of A and then the class name, because ImageNet is just like a image classification data set. But then there's also this CC 12 million data set that has 12 million text image pairs and has a lot of like long tail visual concepts within there. So that's kind of like the labeled data that they have. But what I thought was interesting is they also have synthetic data pipelines that we're seeing over and over in these newer state-of-the-art models, where basically what they say is that if you think of where these data sets came from, a lot of it was just scraped from the web and like images and their alt tags. And they say that humans are actually like pretty simplistic when they write captions. So they don't tend to go into things like describing the foreground and the background and the composition of the scene and like all different things that people would want to do when they're prompt engineering. So basically what they did is they took an off the shelf state of the art vision language model that could caption images, and then they prompted it to be very descriptive about the foreground and the background and the composition of the team of the scene. And so they generated a bunch of synthetic captions on the existing data. And then they said it was a 50-50 split between synthetic captions and real human captions, which is pretty high ratio, in my opinion. It's kind of cool that we're seeing this pattern over and over again of like, okay, you want more descriptive captions? Let's run like a state-of-the-art captioning model to generate synthetic data. Or in the case of O1 that we talked about at the top, they're using synthetic data to generate like a bunch of chain of thought reasoning that then they can go train the subsequent model on. So like, even though the synthetic data is stuff that these models already know, the fact that you're kind of like guiding the synthetic data to have specific qualities improves the downstream models and kind of like helps hone in these foundation models on more specific types of functionality. They also do a bunch of data pre-processing. So they filter out like not safe for work images, images with low quality, and they deduplicate the data using semantic clustering and deduplication techniques. So you can think of just like computing embeddings for the entire data set. If there's a ton of images in the same semantic embedding space, they try to deduplicate with some threshold. And they also mention before the pre-training, since they are just training this little section within here, they pre-compute all of the embeddings for all of the raw images with that autoencoder, and that autoencoder is fixed during training. So pre-computing all of the embeddings just saves them a bunch of compute during the train cycle itself, because you don't have to run the forward pass of the autoencoder every single time. So that's another just like tactical thing. Speed up training by just like pre-computing all the embeddings there. Um, okay, cool. So let's kind of like dive into results. That's kind of the TLDR is they use synthetic data for improved captioning. They have this multimodal diffusion transformer block that takes in the text and the images and has separate pipelines that kind of communicate to each other through attention. And then they have this rectified flow equation that's really just like a linear equation to help guide it to be straight when it's choosing its trajectories. So that's kind of it. Um, and so they did a lot of the hard work for us, testing out different trajectories. Like I showed in the paper before, like they had a bunch of different variations of the rectified flow itself in terms of different hyperparameters that they put in there, but they also benchmarked it against the EDM and the V linear, and I forget what all the cosine EDM ones. And this rectified flow consistently showed up at the top, and then they also have some specific hyperparameters they used within there to make it better. And typically, when you evaluate these image generation models, it's kind of hard to do it programmatically, but they have some interesting tips and tricks that they did here to help. We've talked about FID score in the past, which is basically like a fidelity score based off of later layers within a neural network. You can kind of look that up in a past dive if you want more information there. But the cooler one that they had in this pipeline was called Gen Eval. Uh, and Gen Eval, I thought was actually super clever. It's a paper in itself, and basically they do the text to image pipeline with some kind of like templatized prompts where they know that it has colors and objects and some sort of um, location type information. And so they'll run the text to image model, and then they'll run an object detection model on the output. And they'll be like, was there an umbrella? Was there a backpack? And are they the correct colors? And are they in the correct places? And so this is a clever, just kind of like using models to evaluate other models way to evaluate generative image models. And so they publish results on that. And what that result set kind of looks like is there's a score for single objects, there's a score for multiple objects, there's a score for if you provide a count, like 4 umbrellas, how well it adheres to the count, how well it adheres to the color, position, and color attribution. I'm not sure what the difference is there, but you can see that uh, using this technique and comparing it to public and private models, their technique comes out on top in all of these different metrics. And you can even see there's like their base model, and then there's even a further fine-tuned one with DPO that actually does the best out of all of these. So that being said, let's look at some results. I've actually been trying to collect a data set to fine tune this model on. And so I was hoping that we could fine tune the model to generate icons that are similar from our website. So I just like grabbed all of the icons from our website and generated some prompt pairs. That experiment is still in progress, and I'll kind of show you guys the results next Friday when it's done. But I also, as I was reading the papers, I was collecting all of the prompts that they had, either in like the appendix or within here, because I thought it would be fun just to like run all the prompts from this paper through the Flux model and any models we want to do in the future, and kind of like look at the results there. And you can see this is Flux Schnell. They released like three different versions. Schnell is the super small open source one. There's a dev one that's a little bigger, and then there's a pro one that you can only run via their API. But even the small one, like a photography of tabletop with a vase of flowers on it, is super high quality here. We can kind of like click through some of these, but I mean, I'm super impressed. A book with the words "Don't Panic" is this one. Uh, Bald eagle made of chocolate powder and mango whipped cream. Like it's pretty crazy that this is just a open source model that you can download and run now. So encourage you to check it out. It's even the inference time on this small model, I populated it here in this column, and you can see it's like under a second to generate some of these images. Some of this might just be like the GPU load of the API I was using, but relatively quick, and super high quality results there. For next Friday, I just want to give you guys this as a jumping off point, but I was using this AI toolkit to fine tune the model. And it's pretty straightforward. You can just give it like a config file. So let's look at Flux 24 GB. This is like, so you could spin this up on an A10 with 24 gigabytes of VRAM and train this thing. And basically, you can tweak the LoRa parameters here. You can pass in whatever base model you want to start with. And then I had to turn on this low VRAM equals true to get mine to work. And then you give it a bunch of prompts that you kind of want to test during the training loop, and it'll generate some images as it's going along, so you can debug as you're going along. So show you guys, I was tweaking the size of the LoRa, the learning rate, and the data set we were passing in. And I'll have more stuff to show you there next week. But yeah, super promising, super fun model to play around with, and pretty awesome that it's open source. Thanks y'all if you're watching on the YouTubes. I'm gonna kill the recording and we can just kind of like chat async here if people have any questions. And yeah, thanks for joining.